The verses of William Shakespeare are most commonly written in Iambic Pentameter. As an example, let's look at Act 1, Scene 1 of Richard III. Now is the winter of our discontent made glorious summer by the son of York, and all the clouds that loud upon our house in the deep bosom of the ocean buried. In Macbeth, the three weird sisters use the Trochaic Tetrameter when chanting double, double, toil and trouble, fire, burn and cauldron bubble, fillet of a fenny snake, in the cauldron boil and bake. My presentation today is not on Shakespearean verses, but on the rise of bubbles, not necessarily in cauldrons, but in chemical reactors. About 500 years ago, Leonardo da Vinci summarized his observation on the motion of air bubbles in a liquid. He wrote about the sinuous movement a bubble follows as it rises through the liquid. And this is the original drawing of Leonardo. Let's first confirm Leonardo's observations by following the bubble rise in water, filmed using high-speed camera equipment. Indeed, we see the sinuous and tenuous movement of the bubble as it rises through water. About 30 years ago, we, in a paper published in Nature, simulated or attempted to simulate the observations of Leonardo da Vinci by performing simulations using computational fluid dynamics. Here I show video animations of the simulations for a 4 millimeter bubble rising in water, 5 millimeter bubble rising in water, 9 millimeter bubble, 12 millimeter bubble, and 20 millimeter bubble. Let's start with the 4 millimeter bubble. And we observe the sinuous motion reported by Leonardo and also observed in experiments. Let's go to the 5 millimeter bubble. Sinuous again, which is a little bit on the larger side. The 9 millimeter bubble is slightly different. It appears to behave like a jellyfish. And breaks up in the computations at least. Let's look at the 12 millimeter bubble. It appears it rises by like a bird flapping its wings. Let's look at a 20 millimeter bubble. First it sheds off its edges and rises like a spherical cap. After performing the simulations reported in this paper, we went to the laboratory and with the aid of a high-speed camera, tried to track the bubble motion as it rises through a liquid. Different bubble sizes were injected into the bottom of the water column, and the trajectory was followed with the camera. And this is what we find for a bubble of about 4 millimeters. We can call this a Leonardo bubble. It's a 5 millimeter bubble, also following a sinuous movement, but appears to be more flexible and fragile. Here are bubbles injected quickly one after the other, so that they try to follow the leader. Again, sinuous motion. A slightly larger bubble behaves like the jellyfish that was observed in the computational fluid dynamics simulations. Let's increase the bubble size a little bit more, and we see a little bit of the flapping of the wings observed in the simulations. Here's a 20 millimeter bubble that has the shape of a spherical cap and breaks up, recoalesces as it moves up the column. Let's do another computational experiment. We take a single bubble of 32 millimeters in size and place it in columns of two different diameters, a 5.1 centimeter diameter column and a 30 centimeter diameter column. And let's have a look at how fast a single bubble of the same size rise in these two columns of different dimensions. We note that the bubble of 32 millimeters rises faster in a 30 centimeter column than it does in a 5 centimeter column. This is because of the wall effects that tends to exert a drag on the bubbles, whereas a single bubble in a very large diameter column is free from wall effects. Now, these wall effects or lack thereof needs to be taken into account in scaling up bubble column reactors, because in practice the bubble column reactors could have dimensions that range up to, say, 20 meters in diameter and 40 meters in height. Let's perform another computational experiment in which two bubbles, each of 3.1 centimeter diameter, are placed in a column filled with water, and the column diameter is 5 centimeters. The CFD simulations are carried out assuming axial symmetry, and you see only one half of the column being displayed. Let's see how the bubbles rise. You will note that the trailing bubble has caught up with the leading bubble. In other words, even though the diameters of the two bubbles are the same, the trailing bubble rises faster than the leading bubble. Now, these are computational fluid dynamics simulations. Let's see if experiments show the same. I do experiments in two different columns, two different diameters. In each case, we have two bubbles of the same diameter placed one below the other. Let's have a look. You can see clearly, once more, that the trailing bubble catches up with the leading bubble and coalesces. The explanation is as follows. The leading bubble has a wake which draws in the trailing bubble, and the trailing bubble gets accelerated. This acceleration of the trailing bubble due to wake interactions is exploited by cyclists in the Tour de France. It makes sense to not be the leader of the pack, but to follow the leader so that you can benefit from the wake that is created below or behind the leading cyclists. And that wake helps to accelerate the motion of the trailing cyclists. Only right near the finish line does the trailing cyclist then attempt to overtake the leading cyclist. This is a very common phenomenon, and the explanation lies in the wake interactions. So far we have seen the rise of single bubbles, but in an industrial bubble column reactor, you would sparge the gas in a column of liquid at very high velocities, and you get bubbles of a wide variety of sizes, and you see large bubbles coexisting with small bubbles as they rise through the liquid. What is also fascinating is the similarity of bubbles rising in liquids with bubbles rising in powders. Let's have a look at a fine powder, typically about 50 micrometers in size. And if you take a bed of fine powder and sparge gas through it, you get a phenomena you observe which is similar to that of a liquid. In order to emphasize the similarity, we now switch back to the liquid. This is now again powder. This switching back to liquid to see powder again. And back to liquid. So the bubble rise phenomena in liquids and fine powders are fascinatingly analogous, and this analogy can be put to good use in scaling up bubble column reactors and fluidized bed reactors.